Hey everyone, welcome back to the channel. Today we are going to tackle one of the most important topics in statistics: methods, precision, and sample size determination. Now, I know this might sound technical, but trust me, by the end of this video, you will have a crystal clear understanding of these concepts. Whether you are a student working on a research project, a professional analyzing data, or just someone curious about how statistics works in real world application, this video is for you. So let's not waste any more time and dive right in. Let's start with the foundation: simple random sampling. This is arguably the most straightforward and unbiased method of selecting a sample from a population. Imagine you have a group of 6 people labeled A through F. If you want to select a sample of 3 individuals from this group, in simple random sampling, every possible combination of 3 people has exactly the same chance of being selected. That means combinations like ABC, DEF, or ADF all have equal probability. Now, why is this important? Because this equal probability ensures that our sample isn't skewed toward any particular subgroup within the population. It's like giving every member of the population an equal voice in our study. This method forms the basis of many statistical analyses because it minimizes selection bias and allows us to make generalization about the entire population based on our sample results. Remember, the key takeaway here is that randomness leads to better representation. The more random our selection process, the more confident we can be that our sample accurately reflects the larger population. Now let's talk about precision of estimates. When we take a sample from a population, we are usually trying to estimate something about the population, like its average or mean. But here's the thing: our mean isn't going to be exactly as same as the true population mean. There's always going to be some differences, some error in our estimate. This is where standard error comes into play. The formula for standard error is sigma by root n. What does this tell us? It measures how much our sample mean is likely to differ from the true population mean. Notice that the standard error depends on two things: the population standard deviation and our sample size. Here's something really important to understand. As our sample size increases, the standard error decreases. This makes sense intuitively. The more data we have, the closer our sample mean would be to the true population mean. Sometimes it's helpful to express this error as a percentage of our sample mean, which is what we call the relative standard error. This gives us a way to compare precision across different studies or measurements. The practical implication here is clear. If we want to precise estimates, we generally need larger sample sizes. But as we will see later, there's a balance need to be struck between precision and practicality. Building on this idea of precision, let's discuss confidence intervals. A confidence interval gives us a range of values within which we believe the true population parameter lies. With a certain level of confidence, for normally distributed data, we know that about 68% of the values fall within plus minus 1 times standard deviation of the mean. About 95% falls within plus minus 1.96 times standard deviation, and about 99% falls within plus minus 2.57 times standard deviation. This leads to us the general formula for a confidence interval, which is sample mean plus minus z times standard error, where z is the z-score corresponding to our desired confidence level. Let me give one concrete example. Suppose we have a sample mean of 50 with a standard deviation of 5. For a 95% confidence interval where z-score equals 1.96, our interval would be 50 plus minus 1.96 into 5 equals 50 plus minus 98. So, we would be 95% confident that the true population mean lies between 40.2 and 59.8. It's crucial to understand what this confidence level actually means. A 95% confidence level doesn't mean there's a 95% chance that this specific interval contains the true mean. Rather, it means that if we were to repeat our sampling process many times, about 95% of the intervals we calculated would contain the true population mean. This distinction is subtle but really important for proper interpretation of statistical results. Now, here is a common problem in real world research. What if we don't know the population variance? After all, if we know all about the population, we probably wouldn't need to sample it in the first place. This is where the t distribution comes to our rescue. When we don't know the population standard deviation, we use our sample standard deviation instead, and we switch from the normal distribution to t distribution, especially for small sample sizes. The modified confidence interval formula becomes x bar plus minus t times s by root n. The t value here depends on both our desired confidence level and our degrees of freedom, which is essentially our sample size minus 1. Why does this matter? Because the t distribution has heavier tails than the normal distribution, meaning it accounts for the extra uncertainty that comes with estimating the population standard deviation from our sample. As our sample size grows larger, the t distribution becomes virtually identical to the normal distribution, which brings us back to our earlier formulas. Practical tip here is to always use t distribution table when working with small sample where n is less than 30. Here's one of the most powerful concepts in statistics, the central limit theorem. This theorem tells us something truly remarkable. No matter what shape our original population distribution has, the sampling distribution of mean will become approximately normal as our sample size increases. What does this mean in practice? Even if we are dealing with the data that's skewed or bimodal or has some other non-normal shape, as long as we take large enough samples, we can still use normal distribution based methods to make inference about the population mean. This is incredibly useful because many statistical test and confidence interval methods assume normality. The CLT gives us a way to satisfy this assumption through adequate sample sizes. However, it's important to note that large enough depends on how normal or non-normal our original data is. For highly skewed distributions, we might need larger than 30 for the CLT to work its magic. Finally, let's tackle the big question. How to determine the right sample size? This is where the theory meets practical constraints. First, why does sample size matter? Too small and our results might be unreliable or variable. Too large and we are wasting resources on unnecessary precision. There are three main approaches to determining sample sizes: confidence interval approach, coefficient of variation approach, cost based approach. Confidence interval approach, here Z is for our confidence interval level, sigma is our estimated standard deviation, and E is our desired margin of error. For example, with 95% confidence, sigma equals 5 and margin of error equals 2, we need about 24 samples. Coefficient of variation approach. This is particularly useful when comparing variability across different groups of studies. Here, the sample size becomes C by C of x bar whole square. Finally, the cost-based approach, where F is our total budget, F0 is our fixed cost, and F1 is cost per sample. So the N becomes F minus F0 by F1. The key is to choose the approach that best matches to our study's priorities, whether that's precision, comparability, or budget constraints. Let's do a quick recap of what we have covered. Simple random sampling ensures fair representation. Standard error and relative standard error measures precision. Confidence intervals gives us ranges for our estimates. The t distribution handles unknown variance in small samples. The central limit theorem allows normality assumptions. and we have multiple methods to determine optimal sample sizes. If you find this video helpful, please give the video a thumbs up. It really supports the channel. Drop your questions in the comments below and don't forget to subscribe for more content like this. Thanks for watching and I'll see you in the next video.